So up to now, we've looked at the inputs here. We can look at the table of contents, and we last looked at, in the previous video or previous session, we looked at the distribution of house prices. Now, what you might observe is the bulk of property prices are below the 1 million mark. So using this syntax from Seaborn, we can get a distribution plot where the variable we're plotting is price. And what we're observing here is the bulk of property prices are below or sub 1 million. But then there are the more extreme, and then skewed here to the right, some extreme observations. So if we go back to inspecting the data, right, where we had transposed, when we looked at the property prices, we had 21,613 observations, so that's separate sales. And we saw here that the mean value is 540,000, but the maximum price was 7.7 billion. So there's 7.7 million, which you can see here when we look at the house price distribution. You can see here that these outliers are here, but they're few and they're the more extreme ones. So in our errors, that when we start the model, some of the results that we might get might in fact be outliers. Some of these trophy properties where we have data collected for them might actually create a lot of error in our model, right, and throw the models a bit. So that's something we should be concerned with. Now, when you, another thing you might note here is that when we run go into our Google Colab and look to see where our data is, right, we don't actually have, when you start a new session, right, the data that we were working with, the Kings County data is gone. So we have to load it back in with the new session, unless you hardwire. Now I've left a link here, right, to the data set, and we can just download it as a CSV file, right, and we can download, and it should go in. So this should be in the downloads. Now I've downloaded it earlier today, right, but if we want to get the data in there to run our Google Colab notebook, I have to go to and find that CSV file, which is just here. That's what we just downloaded, but we're going to refer to this KC, Kings County, underline and house .csv, right? And then we can just load in our libraries as usual. We can check where it is. It's going to be in the content folder, so we verified that, and we can read in the data. If I started to run the commands without that file there, CSV file there, then nothing would appear here. So we just check. This is just descriptive statistical analysis. We're looking at just the outputs and so on. So there's no manipulation of data going on here. It's really just looking at what's in our data set. Okay, now when you leave a comment, if we double click here, we leave a comment. That can be quite useful, and that then leaves over here a way to navigate through your project, right? So a house price distribution, that's showing up here in the stubs because that's something that you wrote here in the text. And to create, for instance, if you wanted to create a new line indicating something about house prices, right? If I just write in house prices and then put the asterisk in front, or a hashtag, or the pound sign, then you can see that's gone in there, you see. Now, if that's not adding any value there, we can delete it out, it's gone, and it's gone from here as well. So basically, that's a nice way to track your project. When we looked at living space, then I used the same graph, right? distribution plot, and we got same type of idea that there's some outliers here. So there's some very big properties, but the bulk are probably just around the 2,000 square foot mark, right? And we look at bedrooms then, and we can look at the distribution in terms of count plot of bedrooms, and you can see bedrooms 3, 4, okay, 2, 3, 4. This is kind of the bulk. Probably 3 and 4, the two that stand out for these typical homes, right? We could have a look at, is there a link then between the price and the number of bedrooms? So you could set up box plots. So in each instance, 1 bedroom, 2 bedrooms, 3, all the way up to 33, which is complete outlier, right? That probably is a motel or something. I don't know what it is. Maybe it's an old folks home. Again, I'm not sure. Sold as a residential property, maybe. But seems to be positive correlation between the number of bedrooms and the price, with some kind of, you know, in each instance here, we're getting the median and then the percentiles and the outliers. The most expensive property here, the 7.7 million property that we talked about before, is a 6-bedroom house. Okay, so that's, now when we look at bathrooms, are we getting something similar? That's probably not an ideal way to represent that. So maybe we could look at it using the same syntax as what we have here. So I could just perhaps count plot, copy selection, come back in, take that, and change the syntax a little bit around, right? So we put that here. Now we're using, this is using Seaborn libraries that we invoked before. So let's just Control V and run that. And you can see, okay, bathrooms, there's quite a variety of different, you know, it's not a nice unimodal distribution. Seems to be tri-modal, perhaps some outliers here, but maybe the most could be apartment living, and then, or more apartment style type living, or smaller bungalow type properties, and then bigger houses. And there's 2 distributions or 2 populations, maybe in terms of bathroom. Okay, but could we do something similar in terms of input in something like this, and instead of putting bathrooms, perhaps we could put in, instead of putting bedrooms in, throw into the syntax bathrooms and see what kind of graph we get. Okay, so we could just load in additional little bit of code there, Control V. Now if I run that, I get obviously the same as what I had before. Okay, so there's no point doing that. But remember, the variable here is bathrooms, right? So if I just change here the X, what's on the horizontal axis, to bathrooms, right, we would be able to get a series of box plots, right? And we could look at, is bathrooms correlated with higher pricing? Seems as if it is, right? The more bathrooms you have, the more expensive the property becomes, right? The more expensive the property becomes. Is there a stronger correlation between this and price? I'm not sure, but it's very clear that the more bathrooms you have, the more valuable the property is. The more bedrooms you have, the more valuable the property is. But of course, the higher number of bedrooms and bathrooms also is indicative of higher amount of living space per square footage. Now in Kings County, there's a grading system. It goes from 1 to 13. And again, when we look at this, what we observe is the higher the grade, but typically the average here seems to be about 7. I can check that going back to the data that we had before. So if I look at the descriptive statistics and what we had here, the grade, we have a mean of 7.6, right? The minimum value was 1, the maximum value was 13, right? So 7.6 is the average, and there is a correlation When we go down to grade, we can see there is a relationship between the grade and the value of the property, the price of the property. The higher the grade, the higher the price. Now, we have a figure here of 1, 2, 3, 4, 5, 6. So maybe I could put in 7.5 million or 8 million and run that again, see what happens. Okay, I just see a bigger, I don't truncate the distribution, right? So again, just in terms of our looking at the relationship between grade and price, the most expensive property was about 7.7 million. So putting in a Y max here might be of 8 million probably is okay. So I can capture everything. But if you wanted to see maybe not that many properties or the 8 million, if you want to look at properties maybe up to 1 million, see what's going under the hood, you can adjust that, recalibrate it, and you might be able to see more at a micro level what's going on here, right? But okay, we'll put it back to 8 million. Okay, so then the year in which the properties are built. So we kind of have a histogram then that's giving us, if we're looking at the housing stock and the properties that are sold in between 2014 and 15, and that's what this data set captures. There is a non-trivial amount of property, still legacy property, dating back to the 1900s. And of course, people buy properties, renovate. So, you know, it can be quite modern and insulated and so on. And we see here kind of a drop off here in this period. So the 1900 and 1920, then the 1930s. Now that chunk of property that's missing might reflect the Great Recession, the Great Depression, 1929 to just before World War II, right, was a period of economic recession in the United States. So Seattle may have been affected by that. And then we have 2000, go up to 2000, we have 2020, so we're about 2010. Seems to be a lot of property from just before 2007, 8, then a complete drop off. And then 2014, 15, the amount of property here has gone back up. So this is reflecting economic activity as well. We see the economic depression. We also see here the 2007 crash. Okay, so we've the year the property was built. We can have a scatter graph comparing the living space to the price. That's not a bad way to represent it. We're using Seaborn here, syntax, right? And we're invoking Seaborn library. Fairly clear as we increase the living space. That's the living space of the house, the property. The value of the property is going up. So there's a positive relationship. But then we had a very extreme property, very large, but it's not that expensive. It's 2 million probably. But then there's another property that's a bit smaller that went from 8 million. Now that can throw out, if you're running a model, trying to estimate a model, can you imagine when you put a line of best fit here through your data, maybe the line of best fit would run like that, but this outlier here will pull that line of best fit down, and you may be getting results that are in a linear model that are going to be less good than if you have another type of model. So OLS, ordinary least squares, is a linear model. Random forest might be able to overcome this type of fit, right? It's not a purely linear relationship. It is an ensemble of trees, and basically we can use maybe a more non-linear technique to capture these outliers a bit better. So OLS is a little bit hamstrung in that if we create purely linear relationships between the explanatory variables and the target variable, which in this case is going to be price, then that's going to potentially create a situation where our line of best fit is being dragged down by the outliers. Now, if you're doing maybe an OLS type and you're relying purely on OLS, as a measurement tool, as a way of modeling and fitting your data, then you might start to look at your outliers, and you might exclude the trophy, some of these variables like that, right? You might look to see where are the outliers and can we exclude them, and find for the other variables start dropping out the outliers. So you're doing that for a number of the explanatory columns, picking out outliers, maybe excluding them. That actually can be a lot of work. And sometimes when you throw out the outliers, you're throwing out something in value. It's also fairly clear that the, before I do that, maybe we'd have a look at the square lot, right? Remember the square lot, if we go back to the original set up here, when we explained what the square lot is, the square footage of the lot. So it's the area outside the property, right? And okay, so we're looking at the scatter graph for square footage, living space against price. There's a positive relationship. When we look at the square lot against the price, it's a little bit hard to tell. It's obviously a positive relationship. So if we start here and go out, maybe the line the best fit would look like this. But could be there's more than one or two. There's something else going on here. If you have a very large lot size, it might mean you're out in the country, away from the big urban areas. And that might mean you're away from other interesting, you know, you're living far away. So previously when we looked at, I think the Willow map here, right, which traced out, this is a contemporary current real estate. Zillow is a well-known real estate like Daft or in Ireland, right, or My Home. And you can see if you have a big lot, it might be because you're far out, right? So it just may well be you have a big lot, which is not a big lot in an urban area, but actually in a more rural type location. And despite the fact it's quite substantial in size, the square footage of the lot might be quite substantial, the property price might actually be quite low. Okay, so a couple of things going on. If it's a big lot in, let's say, in an urban area, your property will go up. But if it's a big lot and these are in rural areas, then the property price may not reflect, may not go up. In fact, the big lot just indicating that you're in a more rural location away from urban amenities. We mentioned before that Waterfront, again, using Seaborn library, we graphed using a box plot, the 0, 1. 0 denotes not as close to waterfront or no view of, let's say, the sea or the ocean or a lake or away from a river, right? And those that had the view. And when we look at the median, it's fairly clear that those waterfront properties on average, right? Now there's some that are not that expensive, but the median compared to the median otherwise, where there's no view of the sea or a lake, a waterfront property is worth more. Now you could have issues relating to flooding and so on that you don't get further inland, but all in all, people like to live close to water, it would appear. And again, when you go back to Zillow, right, when we looked at the valuable properties, again, the places close to, if we look at those places that are quite close to water, right, are commanding, there's 14.7 million. Now this is 2021, right? So February 2021. So there is a very substantial increase. That's double the price of the highest property in 2014-15. 22 million, 4 bedrooms, 7 bathrooms, 7,610 square meters. Okay, so these properties that are close to, that have a view of the sea, that are coastal, right, tend to be worth more. The further inland you go, right, those properties come right down. There's 2.7 million, so on. So if you're away from this waterfront location, the properties get a bit cheaper, right? So waterfront would appear to be something that's very important in terms of the pricing. Okay, and we can see that. And we did using a scatter plot and the longitude on the horizontal axis and the latitude on the vertical axis, we could see those areas closest to the water, right, commanded the highest prices. So again, you can kind of see the outline here of if we take this map, look at where we have these seascapes and lakescapes, you can see that mirrors here the darker dots where the pricing is higher. For a higher, you can see as we change, the shading becomes darker, the value 1.5 million, 7.5, the value of the properties tend to increase. And we have these clusters of very valuable property, but also close to water. So it seems to be qualitatively something that's very important. Okay, so that's our discussion of latitude and longitude. Then we can look at, let's say, correlation matrix. When you're doing a correlation matrix, typically you're trying to see what is the interrelationships between the variables. And as you can imagine, one might expect that if we look at the price of properties, the darker coloring here denotes positive correlation. The maximum correlation is 1. The minimum would be -1. We don't get quite to -1. Or we, let's see, I think we go to -4. Right? There's a -6. Okay, how do we read this? Well, we could look at the price. We would say, obviously, price is correlated with itself. It is a positive correlation with bedrooms, bathrooms. We saw that before, 0.5. Square living space, the higher the square living space, that's positively correlated with price. Square lot, but again, the bigger your lot, perhaps, the more rural the location. So it's a little bit neutral. It's not quite as clear cut as the square foot living space. The square foot lot is close to 0. Okay, so there's couple of things going on. A slightly positive correlation with the number of floors in the property. The waterfront is also 0.3, but there is a tendency we would suggest that if we have a waterfront, the value of the property is higher, and the view, the number of times the property is viewed, the condition of the property. Again, there's a metric we might have a look in our data here. Check the descriptive statistics in the transpose. If you look at the condition, come down to the transpose. If I can find that, yeah, the condition varies. We have a mean of 3.4. What's the minimum value is 1. The maximum value is 5. So it's some kind of system of determining what state the property is in. Let's just see here, condition. If we can find it, how good the condition is overall. Okay, so it's some kind of metric that's capturing the condition of the property, and it's fairly clear when we come down to the correlation matrix. When we look at the price and compare it to condition, well, actually it's 0. Okay, so maybe what that's suggesting is that if you have a property that's a fixer-up, it maybe, offer opportunities to people. So some people will buy properties not so much on how good, what condition the house is in, it's the location, right? So you might have a property in excellent condition, but if it's in the wrong location, or if you have a house that's in poor condition, but in an excellent location, you might be willing to pay a premium from that property, even despite not being in good condition. Again, It depends on what the condition is capturing. I would say state of what kind of repairs are required in the property. The grading might include other factors like where the property is located and access to amenities, right? And there's a strong, whatever grading system they have, that seems to be capturing quite a bit what's going on with the price. The square footage above, that's above the basement, that's more important than the square footage below. But in each instance, if you have extra place in the basement, it'll drive up your property. But if you've extra space in your living space, but not as basement, it'll drive the property up even more. So people like their basement space, but they like even more that space above basement. The year the property was built, okay, so the newer the property is, the more valuable, but again, it's not, it's quite neutral, right? Slightly positive. Year renovated, slightly positive. The zip code, it's going to be hard to read the zip code, but it may well be that latitude and longitude capture better address than zip code, right? So is it numerical variable? In the end, we do drop the zip code and we rely on longitude and latitude. Now, when we go in and we look at longitude and latitude, let's just take a look at that for a second. So just before, this is our latitude here. So there's a positive relationship. So that suggests the further north we go, the more valuable. I think the properties further south here, right, are less dark. And as we go up further, they're a little bit darker. So that may explain why there is that correlation in the properties, right, between longitude and latitude, between price and latitude. And then living space, I think that's pretty much the same as what we had before, right? The square lot, right? So basically, these variables are quite similar to these ones, except this takes into account maybe there was renovation done. So in 2015, again, according to the plans, according to what you have in 2015, right? So, okay, but they're obviously sharing the same type of relationship. Now we're going to drop some of the variables in terms of if we find out, okay, what's in the columns. If we want to see output, what did we have? We had ID, we had date, we had price, bedrooms, and so on. That's what we've been looking at. But we might, for convenience, drop ID, date, and zip code. And again, you wouldn't do this in every instance, right? So if we take our original data, what did we have in there? We had ID, date, and zip code. And when we apply this syntax, it just says drop out ID, date, and zip code. So they don't appear then in our, right? If we, for instance, do transpose this, run again, we turn it on its side. Okay, maybe that's not really helping. Run again. Drop. So we have to get our DF columns. And then now why we have left something out. So we should have run correlation and output and make sure we have everything in, right? So I better go back through meticulously and make sure I hit all the operations. Okay, inspect each column and sort. So they all look okay, right? So it looks fine in that regard. And then come down. Year built, we have all that. It's fine. And then output our columns, they're fine. And then we want to drop a couple of columns. Okay, now we have an issue. What is the issue? We've already dropped the columns. So once we do that, we can't drop again. So it's looking for ID, date, and zip code. It can't find them. That's why it's saying it's a problem. So if we'd have to start from scratch to load in our data, okay, I'll do that just for the sake of clarity, right? If I run and then say, look, refresh df to be equal to this. This is what df is now, right? So it will have ID, it does have date, and it does have the zip code, right? Wherever zip code went to, zip code is here. Now, when I go down and then say remove those three variables, ID and the zip code, right? Okay, so your bill, let's just check. It's working. Let's just check this one. Seems to be fine. Okay, and let's go down to where we have the issue here. When we run this, when I print this out, notice that I had removed ID, date, and zip code. So that's why they weren't appearing here. ID was gone, the date was gone, and the zip code was gone. If I run this again, they're now here, but that's because I refreshed the data and set df equal to this, right? If I run again and put in transpose, right, our data has excluded. So if I run this again, what we'll see is ID, bedroom, the ID is gone, the date is gone, and the zip code. So we've ID, date, and we have the zip code here. When I run this again, because of this command, it's gone out. And we don't need to run this again. Okay, so there's no ID, there's no date, and there's no zip code. The zip code is gone. One of the reasons why you would exclude the ID, each property has its own unique identifier. If we put this into the model, it will eat up all the explanatory power. So we don't want to use that in our modeling, because in the case of a random forest, it'll just look at the ID and associate the ID with a particular price. And because it's a single unique variable or value that's identifying each property and identifies a price, a random forest will suck this one out, will identify, filter, or put all the explanatory power on ID, which is not that useful. Okay, so it makes sense here to remove that. Okay, now the next thing is we want to set up the ordinary least squares estimation. If you're running ordinary least squares estimation and you want to get some kind of background on how you measure error and so on, my advice is just to go to the OLS element here, right? It's the linear regression, and run through just basically, first of all, an explanation around how we implement ordinary least squares, linear regression, but also how do we compute the R squared and the level of error and the explanatory power. I do that in Excel, I do it in Python, I do it in R. So there's a fairly complete treatment there. And these sum of the squared residuals and total sum of the squares and the explain sum of the squares, the R squared, the adjusted R squared, they're all incorporated in here into the explanation. Okay, so to get back to where we were, then we're in the Kings County, and okay, we have our data set opened up and our Python notebook running. Now, important in running an OLS regression, we need to identify what's our target variable, right? And we need to know what is our explanatory variables. Now we're going to divide up our data set into this lowercase y, which is the target variable, and into our uppercase x, which is an array of everything in our data set. So it's everything here, all these columns, except what? Except the price, right? And then y is just that single column being price. So basically what we're doing is we're filtering, or we're selecting the columns that the explanatory variables include everything except price, and the dependent variable, the target variable that we want to model, is the price. Okay, so we separate those out. Next thing, we again invoking sklearn, which is the way we, it's the library. Now just make sure that I've loaded that library in properly, right? sklearn. Okay, so import in pandas, we import it in. Okay, so we don't have sklearn here. Just to go back, come down to the modeling, and it's a little bit further down. So full regression. Okay, and then linear regression. Make sure we've run this. Okay, so that worked. That seems fine. We've loaded in sklearn. Okay, that's fine, right? So basically what's going on here is the following. It's important that we execute these commands because they're indicating what sections of which libraries we need to use in order to perform certain tasks. And in this instance, what we want to do is very important for the type of model testing and accuracy that we want to obtain. So we're going to evaluate the model accuracy in terms of R², but we're also going to do something else in addition to standard OLS estimation. We're going to split up our data set into a test and train. And so basically we train the algorithm, we estimate the OLS model, the ordinary least squares, using the train data. And then we test, we take that data, we parameterize our model, and then using that model, we predict what the Y value should be based on the testing data. So we're splitting the data up into training and into testing data. That's done in a particular way. We're saying the test size, so 0.3 of the properties are going to be put into the test data. So 3/10 of our data is for testing, and the other 70% is used for the training. And we estimate our model using the training data with our Y and our X. So Y being the price and X being everything else, all the other columns. And we do that with 70% of the data. Then we take the model parameters and coefficients, and then we load in the testing data, and we predict what the Y value should be based on the X test data. The explanatory variables are put into the model, and we predict out what the price should be based on this testing data. And then we use that, the accuracy from predicting using the testing. So it's, if you like, it's in sample, the training data is in sample, but then we use out of sample just to see how robust our model is. It's okay that, it's fine that our model can explain the sample data, but can it explain other observations? And so that's why we're using, this is a more rigorous approach to testing a particular model. Okay, so we split the data apart for testing